You can't solve fundamental problems until you free your mind to perform fearless thought experiments. We are all familiar with Einstein's theory of relativity and its well-established explanation of time dilation, where time slows down with increased velocity. And now I would like to propose an extension to this theory by introducing a framework of 3 distinct time dimensions. Number 1. Einstein explained how the passage of time slows down at high speed, or even stops if we travel at the speed of light. But this is only the half picture of the first dimension of time. In this video, I will explain the complete picture by putting one more clock on the other side. While working on his theory, Einstein faced a paradox. The mathematics of light didn't align with the classical view of time. He had to choose one universal constant: time, or the speed of light. Choosing the speed of light, as evidenced by experiments in Lorenz's work, meant that time itself had to become flexible and relative. Einstein taken Lorentz transformation as constitute. So, the second dimension is related to Lorentz transformation of velocity. Lorentz transformation of velocity explains that if two traveler A and B moving in opposite direction with, for example, 90% of speed of light, although they are moving apart with 180% of speed of light, but still, they will observe each other not moving more than speed of light. This is 100% correct. But once again, this is only the half picture of second dimension. Get ready for the reimagination, and for the first time, the real-world visualization that how the Lorentz transformation actually works in space. I will explain this by putting one more third clock. The third dimension is, as thought experiment, we have the concept that if something travels towards us with the speed of light, we cannot observe it until it reaches us, is correct. But once again, this is just half the picture of third dimension. I explain in 100% logical way that how we can observe an object moving more than speed of light, even when in reality, it's moving less than speed of light. In this video, I'm going to explain these 3 dimensions by the help of 3 chicks. So I can call this theory as 3 chicks physics, the 3-dimensional theory of relativity. The classic model of the universe includes 3 spatial dimensions and model of space-time as 4-dimension. Einstein famously used this to reveal phenomena like time dilation. However, now I am going to reimagine this same phenomenon of dilation using 3 different dimensions. Typically, explanations of relativity focus on the frame of reference. In this video, I will shift that perspective to a packet of information. I will demonstrate how information actually travels through space, how we can interpret it using 3 distinct dimensions, and how these dimensions are relative to one another. Before moving forward, let me give a strong logic. Why I am changing the frame of reference with packet of information. Currently, we observe phenomena through a frame of reference. We can squeeze, stretch, or curve this frame, but we don't typically apply the concept of delay to the frame itself. The term delay in frame, or frame dilation, doesn't resonate. However, by shifting our platform to a packet of information, we fundamentally change our observational toolset. This new platform inherently allows for the concept of delay. We can now directly observe and understand the effects of a delay in the packet of information itself. This video will present a novel perspective on a fundamental principle of physics. While I acknowledge that Einstein's theory of relativity, supported by the Lorentz transformations, establishes the constancy of the speed of light for all observers, this presentation will re-examine that conclusion. I will derive the Lorentz velocity transformation not through traditional frames of reference, but through the concept of a packet of information. This shift in foundational perspective challenges our understanding of space and time and aims to demonstrate that while the Lorentz transformations are mathematically sound, the interpretation that the speed of light is constant for all observers was a profound misunderstanding. Let's start with first dimension. Einstein's theory of relativity showed that the passage of time slows down at high speeds and would theoretically stop entirely at the speed of light. Let's see what happens when we place another clock on the far side of space. We'll observe how the flow of information actually works, how it travels, and crucially, how our traveling chick reads and interprets that information from his perspective. Before explaining the first dimension, let me create the full scene, and then I will explain all one by one. To explain Einstein's theory, we typically use a single clock observed by 2 different observers. But I will explain the 3-dimensional theory by using 2 clocks and 3 observers to see how the information flows between them. Let's see how these three chicks can observe the same event of speed of light travel from three different dimensions. This is clock tower A, and this is clock tower B. Both are installed at 1 hour light distance. Three chicks are born at the same time at 12 p.m. in two different places. Chick A and B born at tower A, and chick C born at tower B. At 12 o'clock, when all three chicks were born, both tower lights turned on and their light began traveling through space. This packet of information would reach another place in 1 hour. It means till 1 hour the chicks on both sides cannot see each other until the packet reached them, and when the packet reached, they will see each other with a 1 hour delay, 1 hour past event. Just to clarify, when we look into space, we are observing the past events. For example, the sun is 8 light minutes away from us. If it suddenly disappeared, we would still see it for 8 more minutes until the last packet of light reached us. If a star is 10 light years away and it suddenly disappeared, we would continue to see it for 10 years until its last packet of light reached us. When all chicks were born, their heights were 4 centimeters, and they are growing up at 1 centimeter per hour. At 1 o'clock, all chicks' ages are 1 hour means 5 centimeters. Chick A and B observation. At 1 o'clock, chick A and B will observe that tower B clock time is 12 o'clock, and chick C is 1 hour younger, 4 centimeters. Chick C observation. At 1 o'clock, chick C will observe tower A time is 12 o'clock, and both chicks are 1 hour younger, 4 centimeters. For the purpose of this thought experiment, we will assume a hypothetical value for the speed of light at 300,000 kilometers per second. Furthermore, we will imagine that chick A is capable to fly at this velocity. Now chick A decided to travel towards tower B. This will be very amazing to see how all three chicks observed this event with 3 different dimensions. From 2 p.m. till 3 p.m., both chicks A and B had lunch, and then chick A started getting ready for his journey. Right at 3 p.m., chick A started his journey. Let's see how A observed both clocks while traveling at the speed of light, the first dimension. In all cases, we will observe and focus the time packet by packet coming towards chicks. While traveling at the speed of light, when chick A looks back, he observes that the clock A has stopped ticking as explained by Einstein. The reason is that the packet with information of clock time 3 hours and 1 second is unable to reach him. Along with time appearing stopped at tower A, chick A also sees chick B as not growing, but in reality, the clock is still ticking. And chick B is growing at a normal speed. This information is available in the packet right behind the spacecraft. But as this packet is not reaching chick A, so chick A cannot observe the ticking clock and growing chick B. At the same time, tower B time information packets also traveling toward chick A. For easy understanding, I will put 2 cameras facing both towers. From tower B, the packets reaching to chick A's eyes or camera are hitting at double speed. So he will observe, or camera will record, the tower B clock is ticking at double speed, which means time is running at double speed. In this example video, chick A starts journey instantly with speed of light. So the packet of information will never hit the camera means time stop. But if someone travel with gradually increase in speed, then the packet of information will hit the back camera with gradually delay with increase in speed of travel. The packet of information delay will follow the same curve of time dilation curve, but this is actually the packet of information dilation. As a vice versa, while traveling at the speed of light, the back camera will never receive the packets means time stops. But the front camera will capture the packet at double speed, as camera toward packets and packets towards camera both are traveling at speed of light. With gradually increase in speed of travel, the reception of packets will follow the same dilation and acceleration curve, but in the opposite direction. Don't surprise with this idea. Einstein's statement that speed of light remains the same, irrespective of traveler velocity, was based on Lorentz transformation of velocity, which explains that if 2 travelers, A and B, moving in opposite direction with, for example, 90% of speed of light, although they are moving apart with 180% of speed of light, but still, they will observe each other not moving more than speed of light. This is 100% correct. So Einstein given this statement that the observation of speed of light remains the same irrespective of traveler velocity. For now, please keep in mind that in third dimension, I'm going to re-explain the Lorentz transformation of velocity in an easy way by showing that how actually the packet of information flows in the space and the observation remain under 100% of speed of light. You will realize that the Lorentz calculations are correct, but Einstein's statement is needed to be reconsidered. Come back to first dimension. Chick A started his journey at 3 p.m. And in his observation, the Tower B time was 2 p.m. Actual time was 3 p.m. While traveling, in the next 15 minutes, he will observe Tower B time as 2:30, or in other words, he hit the packet of 2:30. At the 30th minute, he will hit the packet of 3 o'clock. At the 45th minute, he will hit the 3:30, and in 1 hour, he will reach Tower B at 4 p.m. Let's rephrase the whole event. When A started the journey, the time on Tower B was 2 p.m. The 1-hour packets of time information, 2 to 3 p.m., were on the way from Tower B to Tower A. Chick A hit all these 1-hour packets in 30 minutes, and then, in next 30 minutes, he hit the next upcoming packet of 3 to 4 p.m. Another example is, suppose Chick C has a flashlight, and he is emitting a flash after every 1 minute. It means he will make 60 flashes in 1 hour and 120 in 2 hours. As Chick A and flashlight both are traveling towards each other, so Chick A will observe flashlights after every 30 seconds. In 30 minutes, he will observe 60 flashes and 120 in 1 hour. In other words, he will observe 2 hours in 1 hour. As we know, both clocks are actually running at normal speed. However, from Chick A's observation, time appears stopped at one end, Tower A, and running at double speed at the other end, Tower B. These observations are unique to Chick A's perspective. Throughout the journey, time around Chick A progresses at a normal rate, meaning there is no effect on Chick A's aging process. After 1 hour, when Chick A reaches Tower A, it will have aged normally, reaching a height from 7 to 8 centimeters, equal to Chick C. You might believe that some high-speed travel experiments prove the effects on the human body, but consider this. Light travels 1,080,000,000 kilometers per hour, whereas an experiment conducted at 1,000 kilometers per hour only represents 0.0000001% of that speed. Given such a tiny fraction, the results could stem from other factors. For now, disregard those experiments and assume everything occurs naturally. I also have a strong reason why time around Chick A should be considered normal. While Chick A travels from Tower A to Tower B, his clock stops at 3 p.m. Upon reaching Tower B, time resumes at its normal rate. If you argue that Chick A should stay younger because his clock was frozen for an hour, you must also account for the fact that Tower B's clock was running twice as fast during that time, meaning Chick A should age twice as quickly. You can't have both outcomes simultaneously. Chick A cannot be both younger due to a stopped clock and older due to a sped-up clock. Either accept both effects canceling each other out or ignore them entirely. The simplest solution is to assume time flows normally and Chick A ages naturally. Okay, come back to the point. The key observations of Chick A's journey. Number 1. Initial observation. Start of journey at 3 p.m. Chick A's height, 7 centimeters at Tower A. Observe Chick C's height, 6 centimeters, appearing 1 hour younger. Tower B's clock, observed, 2 p.m., while actual time was 3 p.m. Number 2. After 1 hour, Chick A at Tower B, time 4 p.m. Chick A grows to 7 centimeters to 8 centimeters. Observe Chick C grows at double speed, from 6 centimeters to 8 centimeters. Tower B's clock ticks at double speed, showing 4 p.m. Reality, only 1 hour passed, 3 p.m. to 4 p.m. But Chick A perceives it as 2 hours due to receiving information at double speed. Number 3. The meeting point, Chick A reaches Chick C. Both Chick A and Chick C are now 8 centimeters tall. Tower B's clock shows 4 p.m., aligned with Chick A's observation. Time dilation effect, speed of light travel, A. While moving at light speed, Chick A observes that time frizzed at Tower B. Chick B's growth paused. B. Upon arriving at Tower A, when Chick A looks back, he sees Tower B's clock resumes ticking. Chick B appears 1 hour younger than reality. C. Reality, at Tower A, time progresses normally. Summary. Chick A's high-speed movement distorts his observations. O. Time and growth appear faster for Tower B's and Chick C. O. At light speed, time seems to stop for Tower B until Chick A stops moving. In reality, time and growth proceed normally. Only Chick A's perception is altered. So, in essence, what we perceive as a delay in time, and really just a delay in the packet of information. Similarly, when time appears to run twice as fast, it's simply because we're receiving that information at double speed. But in reality, everything is happening normally and naturally. Time itself remains unchanged. This first dimension is simple to grasp, but brace yourself for the second and third dimensions, where things get even more compelling. What's coming next is backed by stronger evidence, solid reasoning, and truly mind-blowing observations. Let's move to second dimension. In first dimension, I explained that how Chick A completed his journey started at 3 p.m. and reached at Tower B at 4 p.m. Now I will explain that how Chick C observes the whole event of Chick A traveling at the speed of light. You remember, right at 4 p.m., Chick A reached to Tower B. At that movement, the actual time at both Tower A and B was 4 p.m. Now, in Chick C and A observation, the time at Tower A is 3 p.m. Once again, do you remember that at 3 p.m., Chick A was started his journey from Tower A? Is it surprising? Does Chick A is available at both towers at the same time? The simple answer is no. Does Chick A able to see himself at Tower A as past event? The simple answer is, once again, no. Let me explain the whole event second by second or packet by packet. 1 minute before 4 p.m. at 3:59. In reality, the Chick A is going to arrive at Tower B in 1 minute, but in Chick C observation, Chick A is ready to start his journey from Tower A. Time is 2:59 p.m. To understand the whole event, I will explain the event in double vision and compare the event as reality versus Chick C observation. Now we go back to 3 p.m., when the actual time on both Tower A and B was 3 p.m., and compare it with Chick C observation, which means 2 p.m. When Chick C observed Tower A as 2 p.m., he observes that Chick A and B has started their lunch. But in reality, right at 3 p.m., Chick A pushes the start button to begin his journey. Observation. After 15 minutes, in Chick C observation, Chick A and B were still having lunch and Tower A time is 2:15 p.m. But in reality, Chick A already traveled 15 minutes. Observation. After 30 minutes, he saw that Chick A and B had just finished their lunch. But in reality, Chick A already reached halfway through his journey. Observation. After 45 minutes, he saw that Chick A is getting ready for his journey. But in reality, Chick A already completed 75% of his journey. Observation. After 59 minutes, Chick C saw that Chick A is almost ready to start his journey. But in reality, the Chick A is going to arrive at Tower B in 1 minute. Now let's see the event packet by packet. I am explaining the event in a very simple way, so please be natural. See this event in simple and normal way. At 2:59 and 55 seconds, Chick C saw that Chick A is about to leave in 5 seconds. But in reality, the Chick A was about to reach Tower B in 5 seconds. Now we focus on the last 1 second before 3 p.m. on Tower A or 4 p.m. on Tower B. In Chick C's observation, right at 3 p.m. on Tower A, Chick A pushes the button to start his journey, and suddenly Chick A disappeared from Tower A and appeared at Tower B in less than a nanosecond. Chick C was surprised by the sudden disappearance of Chick A from Tower A and its appearance in his place. And he also saw that when Chick A disappeared, his height was 7 centimeters, but he appeared in his place with 8 centimeters height. Chick A, 1 hour travel time, had completely vanished for Chick C. Let's again rephrase the event by packets of information. Right at 3 p.m., when Chick A pushed the button and started his journey, he was traveling within the packet of 3 p.m. information. After leaving the place, the packet right behind him showed that Chick B doing bye-bye, but Chick A is not in the frame or packet, so all packet behind him were without him. And the packet in front of him at 2:59:59 is showing that he is about to push the button, which means Chick A is traveling right behind the push button packet, and all packets behind him are with Chick B only. The distance among these 3 packets is less than a nanosecond. So, when these packets of information reached Chick C, he observes that at 3 p.m., Chick A pushed the button and suddenly appeared at Chick C place. It means that the whole 1 hour travel event of Chick A vanished for Chick C. For 1 hour journey, Chick A gradually grown up from 7 centimeters to 8 centimeters. But for Chick C, this 1 hour event squeezed into less than a nanosecond event. Almost vanished. For Chick C, the Chick A disappeared from one place and appeared in another place in less than a nanosecond. But hold on, the second dimension is not over yet. Now we look at the same event with 99% of speed of light, or 36 seconds delay in travel time. In this case, with 99% speed of light, the Chick A will reach at Tower B in 4 o'clock and 36 seconds. Once again, let's see the event packet by packet. At 2:59:55, just 5 seconds before 3 p.m. on Tower B, Chick C saw that Chick A is about to leave in 5 seconds. But in reality, the Chick A was about to reach Tower B in 5 plus 36 seconds because he is traveling at 99% of speed of light. Observation. Right at 3 p.m., Chick A pushes the button to start his journey, but in reality, Chick A is going to reach Tower B in 36 seconds. At 3 o'clock and 9 seconds, Chick C will observe that Chick A completed 25% of his journey, but in reality, Chick A is going to reach in 27 seconds. Time on clock B is 4 o'clock and 9 seconds. At 3 o'clock and 18 seconds, Chick C will observe that Chick A completed 50% of his journey, but in reality, Chick A is going to reach in 18 seconds. Time on clock B is 4 o'clock and 18 seconds. At 3 o'clock and 27 seconds, Chick C will observe that Chick A completed 75% of his journey. But in reality, Chick A is going to reach in 9 seconds. Time on clock B is 4 o'clock and 27 seconds. At 3 o'clock and 35 seconds, Chick C will observe that Chick A completed almost 97% of his journey. But in reality, Chick A is going to reach in 1 second. Time on clock B is 4 o'clock and 35 seconds. At 3 o'clock and 36 seconds, Chick C will observe that Chick A arrived at Tower B. The interesting thing to be noted is that total distance is 1 hour, means 60 times 60 equals 3,600 seconds. But Chick C will observe that Chick A completed his journey in 36 seconds, 100 times faster than the speed of light. While we know that Chick A traveled at 99% of the speed of light, the question is, why Chick C observed the whole event in 36 seconds? In other words, how does the 1 hour travel squeeze into 36 seconds? Total 1 hour travel time in seconds is 3,600. Let me put flags on 3 points of travel time. 25% means 900 seconds, 50% means 1,800 seconds, 75% means 2,700 seconds, 100% means 3,600 seconds. When Chick starts his journey, the packet of pushing start button was traveling at the speed of light. In 15 minutes means 900th second, this packet will hit the first flag of 25%. But as the Chick A was traveling at 99%, so he is 9 seconds behind that packet, and he will hit the flag after 9 seconds. In the next 15 minutes, the start push button packet will hit 50% flag, but now Chick A is 18 seconds behind. One more thing to add is, when Chick A hit the flag, that packet is also now traveling at the speed of light, right 9 seconds behind the start button packet. After 18 seconds, Chick A hits the 50% flag, and this packet also started running in front of Chick A. In the next 15 minutes, start button packet will hit 75% flag. Chick A hitting first flag packet is 9 seconds behind. Chick A hitting second flag packet is 18 seconds behind, and Chick A is 27 seconds behind. After 27 seconds, Chick A hits the 75% flag, and this packet also started running in front of Chick A. And finally, in the next 15 minutes, the packet of start button will land at Tower B, and Chick B observed that Chick A started his journey. At this point, Chick A hitting first flag packet is 9 seconds behind. Chick A hitting second flag packet is 18 seconds behind. Chick A hitting third flag packet is 27 seconds behind, and Chick A is 36 seconds behind. Now, focus 36 seconds. When 3 p.m. packet reached to Chick C, he observes that Chick A has started his journey. After 9 seconds, he will receive the packet of 25% flag. In 18 seconds, he will observe that Chick A completed 50%. In 27 seconds, 75%. And at 4 hours, 0 minutes, 36 seconds, Chick A will land at Tower B. In this way, the whole 1 hour journey is squeezed in 36 seconds. It means objects may appear to be moving faster than light, or events happening faster than expected time, but in reality, they're not. By the way, in this 36 seconds, Chick C will also observe that Chick A grown up 7 to 8 centimeters in 36 seconds. Now let's move to the third dimension and get ready to see, for the first time, that in reality, how Lorentz transformation of velocity actually works to observe high-speed travel. Let's see how Chick B observed this whole event. Third dimension will support dimensions 1 and 2 and make it easier to understand the balancing of all 3 dimensions. Let's go back to 2 p.m. at Tower B and 3 p.m. at Tower A. Chick A started his journey right at 3 p.m. Shortly, Chick B realized that Chick A is not traveling at the speed of light. After 15 minutes at 3:15, Chick A should cover the 25% distance of his journey. But Chick B observed that Chick A completed only half of the expected journey, means 12.5%. At 3:30 p.m., Chick A should be on 50%, but Chick B observed that Chick A completed only 25% of his journey. It means in Chick B observation, Chick A is traveling exactly half of the speed of light. Remember, in Chick A observation, the clock ticking at double speed, but here Chick B observed that Chick A is traveling at the half speed of light. The question is why Chick B observed that Chick A is traveling at the half speed of light. The following explanation will easily explain how Lorentz transformation of velocity is almost correct and how it actually works in the real universe. Let's go and watch the event packet by packet of information. Chick A installed a flashlight on his spacecraft. While traveling towards Tower B, he is emitting a flashlight after every 1 minute. So during his whole journey, he will flashlight 60 times. Now, let's see how Chick B observes these flashlights. Chick A starts traveling at 2 p.m. according to Tower B's clock. After traveling for 1 minute, Chick A emits a flashlight. The flashlight takes 1 additional minute to travel back to Chick B. Therefore, Chick B observes the first flashlight at 2:02 p.m., Tower B's time. When Chick A traveling toward Tower B, the packets of information from Tower B were also traveling towards Tower A. So, after 1 minute, the packet of 2:01 was already reached to Tower A, and the packet of 2:02 was passing through the Chick A. So when Chick A makes the flashlight, this flash tagged with packet 2:02, the same packet of 2:02 observed by Chick B at 2:02 p.m. Continuing with the same pattern, Chick A traveled 1 more minute and emits a flashlight tagged to 2:04. Chick B observed the second flashlight at 2:04 p.m. In this way, Chick A makes 60 flashlights in 60 minutes, but Chick B observes each flashlight after 2 minutes. So Chick B sees 60 flashlights in 120 minutes, means 2 hours. This means Chick B observes Chick A moving at half speed of light, taking 2 hours to reach Tower B, arriving at 4 p.m., same as in dimensions 1 and 2. Do you remember? In first dimension, I have given an example that Chick C emitting flashlight after every 1 minute. So here Chick B will observe Chick C emitted flashlight after every 1 minute. And Chick A emitted light after every 2 minutes. So one more interesting thing is, the Chick B will observe that the growth of Chick A is also reduced to half. It means that in 2 hours, the Chick will grow up 1 centimeter instead of 2 centimeters in 2 hours. So when Chick A arrives at Tower B, he will be 1 centimeter younger for Chick B, and he will observe that Chick A and C have the same age. But the question remains the same, how he observes that Chick A is traveling half of speed of light. Now get ready to visualize how Lorentz transformation of velocity actually works or is observable in high-speed travel. I will give 2 simple examples. First is short example, the second with little bit more in details. And for deep details, you can read my book, 3 Chicks Physics, the 3-dimensional theory of relativity. First, the short example is, if Chick A travel with 100% of speed of light and reach his destination in 1 hour, the Chick B will observe that Chick A completed his journey in 2 hours. Observational accuracy down to 50%, 1/2. If Chick A travel with 50% of speed of light and reach his destination in 2 hours, the Chick B will observe that Chick A completed his journey in 3 hours. Observational accuracy will be 66.667%, 2/3. If Chick A travel with 25% of speed of light and reach his destination in 4 hours, 100%, the Chick B will observe that Chick A completed his journey in 5 hours. Observational accuracy will be 80%, 4/5. If Chick A travel with 10% of speed of light and reach his destination in 10 hours, 100%. The Chick B will observe that Chick A completed his journey in 11 hours. Observational accuracy will be 90.909%, 10/11. If Chick A travel with 1% of speed of light and reach his destination in 100 hours, 100%. The Chick B will observe that Chick A completed his journey in 101 hours. Observational accuracy will be 99.01%. 100/101. It means as much as Chick A increases speed from 1% to 100%, the Chick B observational accuracy is going down from 99.01% to 50%, relative to 1% to 100%. Now let me explain this with a little bit more in details. Light travel around 300,000 kilometers in 1 second. Chick A want to travel 300,000 kilometers by car. Suppose Chick A is driving the car with speed of 1,000 kilometers per hour. Means 1,000 kilometers in 3,600 seconds. 60 minutes times 60 seconds. To travel 300,000 kilometers, Chick A needs 1,080,000 seconds. 3,600 times 300. When Chick A reaches the target point 300,000 kilometers, he makes a flashlight. That flashlight took 1 second to reach back to starting point. The chick B standing at starting point, he will observe that chick A make a flashlight at 1,080,001 seconds instead of actual 1,080,000 seconds. So in his observation, chick A travel speed was 999.99907 kilometers per hour, actual speed divided by observed speed. The chick A observational accuracy has gone down from 100% to 99.9999907%. And the delay of information is 0.0000926. This dilation is too minor. The accuracy is almost 100%. Now suppose chick A have a spacecraft that can travel at multi-speed. If chick A travel at speed of 1,000 kilometers per second, means 3.6 million kilometers per hour. He will need 300 seconds to reach the destination, and flashlight will travel back in plus 1 second, 301. It means even traveling at 3.6 million kilometers per hour, the chick B observational accuracy is only down to 99.667%. 300 divided by 301 equals 99.667. The delay of information is only 0.3322%. If chick A travel at speed of 10,000 kilometers per second, 36 million kilometers per hour, he will need 30 seconds to reach the destination, back in plus 1 second, 31. Even traveling at 36 million kilometers per hour, the chick B observational accuracy is only down to 96.774%. 30 out of 31 equals 96.774%. The delay of information is still only 3.2258%. With speed of 100,000 kilometers per second, 360 million kilometers per hour, chick A will reach in 3 seconds, flashlight will back 3 plus 1 equals 4 seconds, the observational accuracy will down to 75%, 3/4 equals 75. The delay of information will be 25%. With speed of 300,000 kilometers per second, chick A will reach in 1 second, flashlight will back 1 plus 1 equals 2 seconds. B observational accuracy will down to 50%, 1/2 equals 50%. The delay of information will be increased to 50%. Look at this table. Even with highest level of speed of light travel, the observational accuracy is down to 50% maximum, and the delayed information is reached to 50% maximum. If we create the packet of information delay curve for chick B observation, it's like the same time dilation curve, but the maximum moving away observable speed reaches to 50% only. For chick B, the observational accuracy down from 100% to 50%. The delayed packet of information maximum reached 50%. Now chick B decided to travel in opposite direction. In his observation, the chick A is already moving away with 50% of speed of light. So now, as much as chick B increases velocity, he will observe that now chick A is moving away. Speed is increasing more than 50%. For example, 51%, 52%. Even if chick B travel at 99% of speed, his observational velocity will not cross 100%. Now the curves will be like this. To calculate the chick A velocity and chick B observation, you need to add both delayed information. Onward, I will show the calculations table. But here you can see that even combining the chick A and B velocity, the chick B observational accuracy never crosses the 100% of speed of light. Here is the table. I have added 2 more columns, G and H. To calculate the chick B observation, first you need to select the chick A speed. For example, above, I selected the maximum speed around 300,000. At this speed, the observable delayed velocity is 50%. So I put 50% in column G, and now I need to add chick B velocity. Now consider column A is the chick B velocity. You can see even if chick B is traveling at the speed of 299,000, the chick A velocity and chick B observation reach up to 99.916%. If we select chick speed 100,000, the calculation will change accordingly. With 10,000 speed, the calculation will be like this. You can see that in all cases, chick A's speed never exceeds 100% in chick B's observation. This is similar to how the Lorentz transformation works in special relativity. However, you may have noticed a difference between my simplified calculations and the relativistic approach. At 10,000 kilometers per second, My estimate is 6.45% of light speed. Relativistic calculation is 6.66% of light speed. At 100,000 kilometers per second, my estimate is 50% of light speed. Relativistic calculation is 60.05% of light speed. All the time, you will find my figures are less than relativistic approach figures. And in some cases, you will find a huge difference between me and relativistic approach calculated figures. The reason is very simple. For example, A and B are traveling in opposite direction with velocity of 10,000 kilometers per second. After some time, chick A flash a light. At this point, we calculate the speed as 6.66%. But in reality, the flashlight takes some additional time to be reached and observed by chick B. This additional time is time decreased the observational accuracy and the observable velocity going further down 6.45% instead of 6.66%. Same in all the cases, you will find the lower percent as compared to relativistic approach. In this way, we can calculate the flow of information, observation, anytime, in any direction. Not only in 2 dimensions, but any dimension. So these are the 3 dimensions of relativity, the complete picture of relativity. The conclusion of all 3 dimensions is that the observation is all about the flow of packet of information, how we receive the information with delay. In other words, there is no dilation of time, but this is the delay of packet of information.